Welcome to this second video in our psychrometrics series. Today we'll dive into the invisible mechanics of air and water vapor, how they behave, how they mix, and what physical laws govern their interaction. This is the science behind every psychrometric calculation we do in HVAC. Here's what we are going to explore. First, we'll introduce Dalton's law and why it matters for understanding moist air. Then we'll talk about how air and water vapor each behave like ideal gases. Finally, we'll look at how the different properties like pressure, temperature, and volume are interrelated in psychrometrics. Our focus today is on how moist air behaves as a mixture of two gases, dry air and water vapor, and how physical laws help us describe and calculate its property accurately. Have you ever wondered how HVAC designers know how to connect all the dots between air temperature, moisture, and pressure? How can we describe the invisible mixture of gases that we breathe every day in a way that let us model, calculate, and control it? To answer those questions, we relied on fundamental laws of physics, laws that allow us to describe how air and vapor behave separately and together. These laws are the foundation for every psychrometric property we use. Let's explore them now. Dalton's law tells us that in a mixture of gases like air and water vapor, each gas contributes to the total pressure independently. In other words, the total atmospheric pressure is simply the sum of the pressure from dry air and the pressure from water vapor. This is just theoretical. It's fundamental in HVAC. This is not just theoretical, it's fundamental in HVAC. We use it to determine two key properties. The humidity ratio, which tells us how much moisture the air contains, depends directly on the partial pressure of water vapor. We calculate it by comparing the pressure vapor to the dry air pressure using Dalton's law. Similarly, the dew point temperature, the point at which moisture begins to condense from the air, is determined from that same vapor pressure. Knowing the contribution of water vapor to the total pressure helps us predict condensation, which is critical in comfort and system efficiency. Dalton's law gives us the tools to measure, predict, and control these invisible but essential air properties. Both dry air and water vapor can be treated as ideal gases in HVAC calculations. That means that we can use the ideal gas law, here represented as PV equal MRT, or more commonly in our case, PV equal MRT for mass-based calculations. This relationship allows us to connect pressure, temperature, and volume, key variables in any HVAC analysis. Since both dry air and water vapor behave like ideal gases, we can apply this law to each component of moist air, dry air, and water vapor, enabling accurate modeling and system calculations. By combining Dalton's law with the ideal gas law, we can break down moist air into measurable parts. We use this to calculate humidity ratio, partial pressure of water vapor, and enthalpy. Understanding how these pieces fit together is what allows us to draw and read a psychrometric chart accurately. We'll explore how to apply these concepts visually on the chart in the next video. Let's review what we learned. Moist air is a mix of dry air and water vapor. Dalton laws allow us to separate their contributions to total pressure. Ideal gas law help us to relate pressure, volume, and temperature for each component. In the next videos, we'll take what we learned about air-vapor mixtures and put it into action. First, you learn how to read psychrometric charts, a powerful visual tool for understanding air conditions and HVAC processes. Then, We'll explore common HVAC processes like heating, cooling, humidification, and dehumidification. Finally, we'll see how all this connects to real world system design decisions. See you there.